So let's start by talking about strings. In the C language, if I want to maintain an array of characters, then I can go ahead and allocate that array. And let's say I just allocate 5 bytes here. And so I have this array sitting out here for my string. And let's what do I want to do? I guess we can just ignore that in C the strings are null terminated. So let's say that I'm tricking this thing up and instead we'll just have a variable here where we're storing the size. And somewhere I have a pointer, and then that pointer's got the address of the beginning of this memory here. And if I have a routine where I want to read in something, and I'm so self-centered and egotistical, I always use my own name. I don't know if this is going to work so well. Let's see what happens. I'll try this little lasso thing. The T goes in here. The O goes here. The D is here. The other D, whoops, oh, let's leave that. I kind of like that. The other D goes here. And then the space goes there. And now I still have input that I need to get read into my array of characters. So in general, what is the process I'm going to do to ensure that when I'm done, I have Todd Gibson in an array of characters? Yeah.
You could extend the string, maybe reallocate to a mem copy or anything, something like that.
So tell me about reallocate.
If you would just write those strings into the JSON memory location, you don't know what that may be. Why don't write the operating system? So,
right here.
You would need to create like a dynamic char array.
All right.
And then.
Let's stipulate that this right here was dynamically allocated. In C it'd be with malloc, in C++ it'd be with the operator new. Can I simply grab more memory dynamically right here? No, the short answer is no, you can't. There's no guarantee when you do a memory allocation where in the heap it's going to be sitting. So what you have to do is the arduous process of creating a larger array. Copying that way. Copying each of these over, so that's going to copy there. This is going to be copied here, right? And you'd probably use a loop to do it, of course. And then once you've got all the existing stuff copied over, then you've got the extra stuff where you can start oops, and I still don't have enough, so I have to repeat the process over again, maybe allocate 15 the next time, copy all these over, and then that final n, and then I've got 4 bytes left to fill before I have to repeat the process. So when you're doing robust input in C, you know, you ask what is your name, and you type in your name. When you're at the 111 level, what you'd do is you'd probably just create a static array of 100 bytes and trust that their name wouldn't be over that. Of course, that won't fly in the professional world, because that's the definition of a buffer overrun, is someone only allocates 100 bytes for something, and so you overflow that and start writing into memory where you shouldn't be writing, and exploit that and make bad things happen. So it's fairly tedious. It's straightforward. We can understand what's happening here, but it's fairly tedious to create a really robust system for inputting streams of characters like this, and managing them generally. So that is precisely what the string class is doing. Is the string class. So now I go into C++ world. It'll have just take advantage of this. It'll have a variable for the pointer. It'll have a variable for the size. It'll have probably some other internal information. There's probably two numbers here, one for the number of bytes currently allocated to this, and one for the current number of bytes that are being occupied with useful information, right? The length of the string versus the length of the memory. So, where do I want to go with this? I'm seeing all this all out of order. Now I've painted myself into a corner. So let me table this for a few minutes. We're going to come back to this. All right. Getting back to our constants, references, and initialization lists. If I create, do I want to do that, or do I want to go with, I can go with, let me go with the library class, all right? And the library class, somewhere, there's going to be a search engine constructor. And I don't believe I've gotten around to talking about this. So what is the search engine constructor going to do?
Probably read in all the files and save them into your vector or media object.
Right.
All the information, create an object for each one.
Read in each of the 4 files. For each record, create a corresponding object. Push back the object onto the, what do we call the vector? That's part of the search engine. Query catalog. So there'd be 4 loops, 1 loop for each file. Open up the file, start the loop. For the book, you read in 10 pieces of information. So open book.txt, loop while there is stuff to read in. Inside the loop, there's going to be a book has 10 pieces of information. and then there will be a, after that's read in, let's see, that's inside the loop, I guess. Then there'd be a card catalog dot pushback, something like that. Yeah, everyone on board with that? Okay. The way we would do it if we were in the 111 or 211 world, or 311, if we're not in the 511 world, let's look at book.cpp. There are going to be 10 arguments here. So let me say string cn for the call number, string ti for the title, etc. 8 more times. All right, there are 10 arguments there. Then I'm going to do something like this. For the title, subjects, so on and so forth. So what has to be true when you hit this line of code, or when you hit this open curly brace, the very first thing we're doing is we're interacting with this call number variable, which is I guess I ought to make that explicit. Okay, we got that going. So 100% of the time we hit that open curly brace, call number has to exist. Now call number is a string, so that means that this here has to exist. This memory has already been allocated. We don't know how much. There's some default chunk. I'm using 5 bytes here because I've got limited real estate to work with. I don't know, maybe it's like 8K, or maybe it's only 100 bytes. I don't know. You'd have to dig into the standard to find out what a string is allocating by default. Yes?
It seems that default initialized, it always becomes an empty string.
Yes. It would be an empty string, but I'm making a distinction here that there are bytes allocated, and there is no information. As far as the string is concerned, those bytes are allocated but unused. Yeah? So this pointer would have been initialized. There would have been a new statement to allocate, in this example, the 5 bytes. This, let me go ahead and just make this explicit. So this object's been allocated. This would be something like 5, and this would be something like 0. Okay? And then once these two are equal, if there's a need for another, a 6th position, if those two are equal, then it'll go ahead and do this allocation and copy, and then start using subsequent bytes. So this right here is actually calling another member function of the string class. You don't frequently see it done this way, but this is actually syntactically a thing. I can say call number okay. So that line right there will actually compile. That is legal C++ right there. And although this equal sign is a little bit straining on our eyes, by and large, the syntax we're comfortable with. We have an object, we are invoking a member function that's part of that object, right? So that means that there is an assignment operator that was written as a member function of this. What has to happen with the assignment operator? We've got some string called cn. So what is this one called? This one's called call number. Then another one, I'm just going to start doing sloppy writing here. This one's called cn, and this has a pointer, and this pointer is pointing over here, and what it has in it is arts 123.87, whatever the call number is. And it's probably got, I don't know, 30 bytes allocated, and whatever that is, 4, 5, 6, 7, 8, 9, 10, a space, say 11 of them are used. Right? So this CN is being assigned to call number. Tell me about the algorithm for that assignment to occur.
Probably a field by field copy.
Okay, so what I can do is I can easily assign 30 to size, and I can assign 11 to string length. Those are just integers. What about this pointer? Art's 123.87 is larger than Todd.
Maybe if you do a field by field copy, we just copy a pointer value. So
that's right. If you're to do a field by field copy, this memory begins at position 999, and this memory began at position 888. So if you're doing a blanket field by field copy, you would basically be changing this to be 999, and it would be pointing at that. That would be just a straight field, basically a member bitwise copy. And the issue with that is now you have two strings pointing at the same chunk of memory. What should happen when string's destructor is called, when string goes out of scope? It should be called, so just as you'd use new to allocate this, when the string is dying, it should use delete to release it, yeah? So this makeup here is going to be wrong because in this example here, CN is a variable that's going to go out of scope at the end of this member function, whereas call number is not going to go out of scope until the book object itself dies. And since they have different lifetimes, what's going to happen is we hit the bottom of this function, CN's destructor is going to run, we'll release this memory, and now call number's pointing to memory that has not been allocated to it any longer. So you can't simply, you can get away with these kind of bitwise copies for the built-in types, but if it's a complex type, then you have to be a little more aware of what's happening. And the process would be to first release this, so you'd call delete on that to release it. It could be smarter. Here's kind of the dumb way that it'll always work. You call delete to release this, and then you find out the length, how many bytes have been allocated here. Here I've written 30, so now it would allocate a new chunk of 30 bytes, and then it would do a byte by byte copy on 11 of them to get arts 123.87 over in this new memory that's been allocated. Yeah? You'd be a little smarter about it by doing something like if this chunk of memory is actually equal to or greater than this chunk of memory, maybe you don't have to go through the trouble of releasing it. You can simply let it be larger and then just copy this over and then copy those. I guess this one wouldn't change either, but you'd copy the 11 over. So it depends on what the requirements are and so forth. But basically, the bottom line is there's a whole bunch of housekeeping. Yes?
Deep copy versus shallow copy.
Yeah, so the term would be a deep copy, absolutely. All right. So the way this is written, the good old-fashioned way of initializing members inside a constructor is going to, one, call the constructor to bring the call number into existence, right? It would look like this, except it wouldn't have Todd in there. All of that code would run, allocating here. Now we do this assignment, and then it's going to run a delete, and it's going to allocate more bytes, and then it's going to copy each of these bytes over to this new set of memory that was just allocated. So it's very, very inefficient. We want to do it in one fell swoop, and that's an argument for having initialization lists. How can we bring call number into existence differently? And the process you should use, sometimes people get confused as to what to put here. Whenever you're writing an initialization list, just follow this rule of thumb. You have your, sorry, my screen's all mucked up on the left side. All right, so here's my initialization list. You put a colon. All you have to do is list the private data. Call number, title, and put a set of parentheses after each one. The 3 dots are gratuitous. And what's my third one? Subjects, right? So I'd be doing this 10 times with whatever the private data is of book. And I'm ignoring inheritance. We'll have to talk about inheritance separately. But if there were no inheritance, there would be 10 strings here. So then I would put those 10 here, and then I can decide what do I want to initialize each of these with. And you have a great flexibility here. Pretty much any legal expression can go where I have the question marks. So what you could do is you can call a function, right? Anyone remember SRAN from seeding the random number generator? Now I don't know why you would do that. In fact, it probably wouldn't be legal because providing an integer to a string is probably not a legal way to initialize it. But the point is that you can put any expression in here. So I could say get log file name, right? Maybe that's some function that I wrote somewhere, and I call that, and that returns a string, and that's what the call number is being initialized with. You can hard code it. There's no need for it to have to be a variable or a function call. Any legal expression, yeah? In this case, we want to put the contents of this variable here. And probably something like that, and so on and so forth. Now, it no longer creates call number with the default constructor. Now there's been a constructor written where what it'll do is it'll analyze this information here, and it'll allocate based on the size of this, and then it'll do the copy over, and then it'll copy these over. So then there's only one allocation rather than having 2 allocations and a delete and so on and so forth.
Can you explain real quick just what was the difference, the main difference again between using the initialization list and then just simply
This?
like setting?
So let me make a final statement. Once I've done that, then there's no need for me to have these here because call number, title, and subjects are initialized the way we want them initialized. So I'll answer your question in just a moment. Given this, with the kind of code we've been writing, there are a whole bunch of empty bodies in constructors, and that's fine. Is it always that way? No. There are plenty of constructors that have to do things, like maybe you've got some sort of database object, and so the body of the function is connecting to a database and doing some interaction to get some value, or it's opening up a log file, right? There are all sorts of algorithms that need to be run, so there's still a reason for having a body to constructors. But as far as private data goes, frequently the initialization list is going to do the trick. Yes?
Has there been a reason why we haven't been doing initialization lists the whole time, like since all the other classes?
The only reason you haven't been doing it up till now is that there's just a ton of crap in the C++ world, and when I'm struggling with the 111 students getting the chevrons right on Hello World, right, you get the idea. You all are plenty mature now to be able to start eating this stuff. Yeah.
I see how you mentioned we're calling the overall assignment operator. Is it the same as a copy constructor?
It is not the same as a copy constructor. So a copy constructor is a constructor, which means that, so if I take this example, when I'm constructing this stuff comes into existence automatically, right? There's actually there's the allocation of the space for the object, and then there's running an algorithm on that, and the constructor is the algorithm part. So even if I just say, if I go somewhere and I say book BK, there are 2 things happening. One, there's space being, in this case on the stack, space being set aside physically for however much room BK needs. and then the constructor is the algorithm running on that new set of space that was just given. Okay, the copy constructor is going to run the algorithm to allocate this and to copy over from an existing object. It's not the same as the assignment operator, because the assignment operator, this already exists, and the first thing it has to do is clean itself up to be ready for the new information. In this case, it has to release this here and then allocate a new one that is the same size as the existing one.
So the copy constructor creates a new object, where assignment operator just works on an existing object.
Yeah, the difference is that with a constructor, it's brand new. With an assignment operator, the object already exists, so you have to take that into consideration. So there are a lot of questions that come up because of this. What if there are built-in variables? There is no advantage to, or let me rephrase it, there is no disadvantage to me initializing built-in types in the body of the constructor. Using an initialization list doesn't save me anything, because for the built-in types, there's no algorithm that's run. You just set aside the 8 bytes for the integer and bam, you're good to go, right? However, because it's more efficient to use to construct complex objects with initialization lists, for consistency, it's generally desired to shove everything, whether or not it is built into the initialization list. So that's a matter of consistency. So there's no efficiency advantage. It's just a consistency argument for putting built-in types here. In fact, this way of initializing built-in types, that was brought in formally to any way that you initialize a number in C++. So if I say init.cpp, let me put a little code shell here. So the way we're accustomed to doing it is this. Let's see. What did I call it? Okay, it's also valid. Let me comment that out. It's also valid for me to say so that's actually now a valid way of initializing things in C++. Which incidentally is
That with 17 or 14?
what are you referring to?
C++ number?
Oh, you know, it was that way in the early 90s.
As if you're calling the constructor for an integer.
Yeah, but we're using the word constructor charitably, right? There's no code per se that you would crack open and see curly braces in a little function doing something complex. It's also now, I'll be frank, I kind of cut my teeth on C, and I tend to do this stuff. I really don't have a sense for how common this is. I will concede that it is consistent, because for complex types, you know, you tend to do that kind of thing, so you see a consistency there. I don't have a sense for its prevalence of initializing built-in types this way, though.
But since we're programmers and we're lazy, that's one more character.
It is one more character, so and those debates are worth having, particularly if you're using a nice programmer's editor. If you're using an editor that requires a mouse, then all bets are off, because I'll have that parenthesis closed and beyond other things while you're still reaching for the mouse. All right.
So it's basically a syntactic sugar, you can say, for initialization of it.
Yeah, you know, C++ wants to love all comers, so go with what, you know, what your kink is, whether you're an assignment guy or a parentheses guy. All right, enough of that. So now that then brings us to these up here, string, title, etc. These are, as they are written, are local variables. They are copies of strings that were created elsewhere, meaning if I say my ever popular add5 function, right, I have this function and then I have main, and I say integer Bobby equals 10, and then I say add 5 Bobby. We know that that the language has pass by value semantics, which means that on line 14 it jumps up to line 5 and X is created as a copy of Bobby, so the modification to X on line 7 is not affecting Bobby. Right? So this is something that you get early on when you're learning the language. We have a similar phenomenon here, which is CN is a copy of a string that exists elsewhere. So what that means that in order to create my book, do I have my book where I created it? No. When I create my book here, and I have 10 strings on line 21 here, that means that those 10 existing strings are being used to call a copy constructor 10 times to create the 10 strings that are the input parameters to this function. And here we discover a whole nother level of inefficiency that we want to get rid of. And that is, in order to get rid of it, we want to pass these things in by reference instead of in by value. Now, by virtue of that single character there, CN and TI are not their own variables. They're merely referring to on the left pane here, CN is nothing more than another name for call, and TI is nothing more than another name for title. So by virtue of passing it in by reference instead of by value, we have now saved ourselves 10 constructor calls.
And on a big complex program,
Absolutely, you get to dozens and dozens and dozens of constructors, and then you think a lot of things loop millions of times, right? So it does start to add up.
And it's also creating that minuscule amount of memory to store that copy thing, but that could add up over time too.
Yeah, I mean, it's particular for something like string. One of the very slow activities in running an application is the allocation and release of dynamic memory, right? Because there's a whole management of the heap going on, and if you're in some tight loop dealing with, I don't know, dozens of strings millions of times, that's tens of millions of allocations and releases that you immediately get rid of as soon as you start passing things in by reference. Now the danger of this kind of thing, and I don't want to say it's malicious, but it could happen unintentionally, is I might change CN here. And if I do that before, who cares? Because CN is just a local variable. I change it. It's going to go out of scope at the bottom of this constructor. Let's see, let me add a bottom to the constructor. CN is going to go out of scope on line 15. And so if we mess with it, who cares? It's just a little local variable. However, once we're passing it in by reference, anything I do to cn is going to change this variable here. Now, I need you to just kind of imagine the big picture here. In this little toy example, I'm on line 21. I'm just merely creating a variable for reading in a value off a file, passing it in here, using it as an initialized call number, not doing anything else. You know, what's the big danger? Well, in a big complex application where you're provided a class, here, now you're provided a class. Maybe your company paid $10,000 for this coding library from some third party, and they've got, and you can't see the source code. The only thing you can look at are the header files, right? So you have to be able to include them in your own code, and you see that they've got several functions here that pass things in by reference, and you're going, oh man, I don't know if I want to be passing my objects in there. What the hell are they doing with them? They could be changing them. And so that vendor, what they want to do is they want to give you a, now it's certainly possible that the function may be designed to change it. And that's fine. There's certainly those situations. However, if the intention is not to change it, then you want to provide that reassurance by saying that that reference is constant. Meaning, again, this, I don't know if I ever said this to begin with. There are many of you that were here right at the end of the period, and I said some things. So I'm not sure what I said then and what I said at other times. But this is a compile time assurance so that the compiler will help you do the right thing. In this case, you're telling the compiler, I am not going to modify ti in this function. If I try, I guess I should do it to, since I'm dealing with cn here. If I make any attempt to change cn, then I want you to tell me. That's my conversation with the compiler by me putting that keyword there. Okay, the key is this is happening while the compiler is compiling. It does not change the code at all. All it's saying is if I do something like this, it will not compile until I get rid of it. So now if I get rid of it, I compile and I have an executable. Then I do this and I recompile and I get an executable. Those two executables are identical. Const is not changing necessarily what you have as far as the produced executable. Now I have to caveat that a little bit and say the big game in compilers nowadays is not generating code but optimizing code. And it might use some reassurances. If it knows that something's constant, it might go ahead and put it with confidence inside of some speedy register to make things faster, right? All in under the hood optimization things that we don't see. So I have to caveat a little bit about whether that executable is actually identical. But in principle, the check is happening at compile time. You're giving an assurance to the compiler so it helps you while it compiles. Yeah.
Understanding.
Yeah.
Just going mentally.
Go mental. Okay, that's fine. So yes.
So with the const there, we don't need to make the thing that it's referencing constant here. So like call, string call, we don't need to make
This. No, you don't, because look at it as look at. So cn is nothing more than another name for call, right? One analogy to look at it as is as a glove. Cn is a protective glove. So here's call. It puts on the glove while it's inside of the book constructor, and you can't hurt it because it's got the glove on. Once the function ends, then it just pulls out of the glove, and it's still here, the same as it always was. So there's no burden on this object. It's merely a promise on how it will treat that object. Now let's see, let me pull, so that takes us to functions. So we got that, we pass them in, that they'll make those constant. Now that has an impact on the design of our classes, because let's say, let me see, what can my example be? Yes.
So here we have we're passing by reference and it's const. So if it's const, we can't change it. If we uncomment line 11, it won't work.
That's correct. Yeah, const makes lines 11 and 12 illegal.
So in that case, using the initialization list will be our only way of doing it.
Oh, excuse me, I'm sorry, I misspoke slightly. This one's fine. It's line 10. Right? 11, I'm sorry. I'm not seeing it. Here, let me do this so I can see this on my side. Yeah, I need a new screen, but the department can't afford to pay for it, so I'm living with my broken screen on the left.
How much does this like translate to other languages? Like, is this pretty much how it works?
I don't have an answer to that.
I know that like Java doesn't have like initialization lists or like aspect reference kind of stuff.
Right, because I think by default, isn't everything a reference by default in Java? So I think in order to pass something by value, you have to wrap it in a class, and when you pass that, yeah, it's got more reference semantics than C++, so you have different mechanisms there. All right, I'm not going to be able to pull what I want to say out of this example, so I have to change it just slightly. Now let's look at, I don't know, let's say we have some sort of show me book, and then I pass in a book BK, but for all the reasons we've been talking about, I'm going to pass it in by reference for efficiency reasons, and I don't intend on changing it, so I do that. And then somewhere in here I have a bunch of code. I'm going to go ahead and say bk.display. Now, with as much as we've done now, this will not compile. And the reason it will not compile is because the only thing that the compiler sees is now you and I know, well, a display function is just going to print out the data members of book. There's nothing changing in book. That's a safe call. But the compiler doesn't know that, in the same sense that I might say do naughty things, naughty changing things. And then I bring that down here. Right, and you go, oh, yeah, you don't want to call that function in there. So the compiler obviously doesn't have the slightest idea which one's good and won't change and which one's bad, so it won't allow either of them. Because the compiler cannot see the source code to the display function or the do naughty things function, it can't examine that code to determine whether or not it's actually changing the invoking object, whether it's changing BK's call number or BK's title, right? So we have to, at the prototype level, at the declaration level, give reassurance that that function will not change the invoking object. Now, line 24 will be just fine because we promised the compiler that the display function will not do anything to change these private data members. And in fact, how does that work? So you look in, I'm cramming every single thing into this file. This is book.cpp. You have void book : display. It's part of the signature. So you have to put const there. Now we have the source code. So we have a bunch of stuff like this. If we try to do something like this, it won't compile because the compiler, you've given the reassurance to the compiler that you won't change anything here, so the compiler won't let you compile if you do try to change any private data. So that's why the compiler is happy to allow this, because it knows somewhere in the world it had to compile a display function declared with const out here, and that at that point in time it will not have allowed anything like this. So it knows anything that's compiled is safe and only accessing, not modifying the invoking object. Yes?
That only happens because we made the book object const, right?
That only happens because we made the book object const.
Yeah, what
Ye-
if,
it-
passing,
Yeah. So right. It's only required because of this here.
yeah.
Now, the way you get around it is you don't use const at all. And we have evidence of that. You made it all the way to 511 without using const, right? It never gave you any troubles calling these display functions. So now we're stepping up our game. We're making things more efficient, and we are using const. We're using const for this, and this just provides a nice use case for why you have to put const here on your member functions. Okay, and this gets, if you weren't here right at the end, basically after class had ended on Monday, const is now something that you need to be dealing with at the design level. It is not something you deal with at the coding level. Now, part of the evidence of that is this initialization list constant references assignment I gave you. If you've gotten through part of it, at least part of it, you go ahead and you make that. There was a function at the top. What was that function called? For the report, was it show report or something like that? Right? You'd pass that argument in by reference, and then I asked you to make that a constant reference. Suddenly everything broke, and now you had to make reports display function constant. But now that breaks date and time because their display functions aren't constant, so you have to go into those classes and make those classes constant. You can't deal with this stuff at the coding level, or on that toy example, it's a pain in the ass. On a huge application, you don't bust out 100,000 lines and then decide to put in constants. It all happens at the design level. When you're designing them, you decide what the function does, and if that function does not change the invoking object, then that should be a constant member function, right? Once it's there at design level, when you're at coding, you aren't making these decisions. It's all there as part of the design. Okay?
And that's the best practice? Or?
Yes, yeah, absolutely. Anyone who's doing coding properly is designing const correctness. They aren't bolting it on afterwards. And the same goes for this kind of stuff, right? You know it. I hesitate to say at the design level because just by default, if it's a complex type, you're just going to pass it in by reference, and constant reference if it's not going to be changed in the function. Damn, we're out of time again. When do I have the library project due? The 19th? Oh, okay, a week. We have a week. Good. All right, so there's some more things that I want to talk about then that have bearing, at least on this kind of stuff, in the library project. So I need someone to say on Friday, be sure to talk about virtual destructors. That's a very important thing to talk about. Okay? All right, any questions before we break?
Yes. I remember we had a kind of syntax, virtual equals 0, where you have const, you have equals 0.
Give me a line number. Oh yeah. The pure virtual function. I'll talk about that on Friday as well. So remind me, pure virtual functions and virtual destructors. Okay? All right. Then we will see you on Friday.